Go ahead.
Okay, I will introduce the speaker. So thank you, everybody, for coming. Today, we are very happy to have Dr. Haizhao Yang visit us virtually. He's a candidate of the AI position in our department this year. Dr. Yang got his PhD from Stanford in 2015. He was then a postdoc at Duke. After that, he went to Singapore as a tenure-track assistant professor at the National University of Singapore. He's currently assistant professor at the Purdue University. Yeah, today he will talk about something about the machine learning. Haizhao, please.
Thank you very much for the nice introduction. It's my honor to have this opportunity to share my recent research in machine learning plus mathematics with application in many science and engineering problems. Today, I'm going to share one of the story among these machine learning and applications. I'm going to talk about discretization invariant operator learning, including algorithms and theory. So I will explain why we want to have operator learning and its applications and potential impacts in many disciplinary, including medicine study. I will also explain why we need discretization invariant. This is very important to reduce the computational cost in real applications to make machine learning very efficient. I will also discuss some mathematical theory to justify the design of the discretization invariant operator learning. And you will see that I will use neural network to do this operator learning. You will understand how we choose the width, the depth, and the number of samples according to our mathematical theorem to achieve a design accuracy. That's the overall overview of my presentation. If you have any question, please feel free to stop me. So today's talk is within a big picture about data-driven methods for computational mathematics and application in multidisciplinary research. We talk about the difference between the conventional and the data-driven methods. I would say that data-driven methods, they provide a new diagram for solutions and new opportunities for mathematics. In conventional solvers, we might need to study for years to understand how to design solver. It may take months for the coding, but after coding, after the design, the solver is usually accurate, but sometimes it might be very slow. And in the data-driven method, interestingly, the cost for study it's lower. Or in other words, the barrier for using these methods is much lower than the barrier for using conventional solvers. We just need undergraduate level knowledge to learn how to use this method. But of course, to get the methods, to design methods like this for user to use, it might need a lot of research. So what typically data-driven method do to solve problem? Usually we want to learn from data to understand how to solve problem. As you shall see that typically this problem will be transferred to a regression problem, which you can be well understood using undergraduate knowledge. But how to design efficient solver, how to invent new mathematics to justify this solver, it's very challenging. It might take days and months to train the solver to solve the regression problem, but after training the machine to solve that regression problem, the application of the machine usually is very fast. We can quickly get a rough solution to the problem you want to solve. So this is a difference between conventional and data-driven method, and they both have some advantage over the other one. Today, I'm going to focus on data-driven methods. Especially, I will focus on learning operators. This is a very broad direction. if we talk about mathematical operators, then we could have some concrete example to understand this operator learning. For example, we have two function spaces, the x function space and the y function space. The x function space might be some data function space, and the y space might be some solution function space. We want to learn an operator mapping x to y. A very concrete example is to solve parametric PDE, where we have the solution of the PDE as the solution space y, and we have parameters of the PDE as the data function space. Given a parameter function of the parametric PDE, we want to get a solution to the PDE. In other words, we want to learn a mapping from the parameter function to the solution of the PDE. So this is a mathematical operator between two function spaces. And this is the focus of today's talk. Of course, the application is not limited to solving parametric PDE, as we shall see later. And more broadly speaking, we can apply this operator learning to learn how to solve problems. One concrete example is learning how to optimize objective functions for optimization algorithm design. For example, we have a function space, which is the objective function space for optimization problems. To solve optimization, we typically use iterative solver to solve that. And the design of iterative solver is essentially to design some updating rule to update the new guess from the old guess. So if we know the updating rule, which is a function, then we know how to solve the optimization. So learning how to solve essentially is reduced to the problem, learning a mapping between an objective function in the optimization to an updating rule in the iterative solver. So broadly speaking, operator learning can also be applied to learn how to solve scientific computing problems. And even more broadly speaking, we can also apply this idea to learn how to design other algorithms. Essentially, we can think about the X space as a task space. We have a function to describe the task we want to solve. And the Y space is the space of optimal algorithm, just like the updating rule to describe how we solve optimization. In general, we could have some function to describe how we solve a problem. So learning the operator between the X and Y space, essentially learning how to design an algorithm to solve a specific problem. So this is the whole picture to understand why operator learning has high impact in scientific computing. Now let us look at the mathematical statement about the operator learning for mathematical operators. So we have two spaces, X and Y. We typically assume that we have real value functions over some domain in RD. We have an operator between the X space and the Y space. We don't know this operator. We want to learn this operator from finitely many samples. For example, we have a sample set X consisting of some data pair UI and VI, where VI, we assume that it is generated by the operator sampled at location UI, possibly with some noise epsilon I following some distribution. So our task is to learn the unknown operator psi from the sample set X. In deep learning, we typically try to use a neural network denoted by psi n to parameterize the unknown function. Then trying to learn the unknown operator psi is equivalent to learning the optimal set of parameters theta star, such that the neural network psi n can approximate the operator psi very well in the sense of supervised learning. Okay, this problem setting has broad application in science and engineering. For example, in reduced order modeling, we want to learn reduced model from high-dimensional complicated model. Then essentially we try to learn the operators in a reduced model so that we can build differential equation in lower dimensional domain to describe our physical system. And in solving parametric PDE, we also have operator learning as we have illustrated. In solving inverse problem, we typically have an operator mapping the data measurement to the images that we want to reconstruct. So we have operator between the measurement function space to the image function space. In density function theory, which is a very useful computational model in actual structural calculation, we could learn operator from the potential function to density function. And if we have this operator learned, then then whenever we have a new potential, we can quickly map it to a density function that contains crucial information about the physical system. In other imaging application, image processing application, we also have operators mapping the data space to the image space or image space to image space. In predictive data science, we want to learn an operator as a prediction operator that can map historical states of the dynamical system to future states of the dynamical system. We have many important applications in science and engineering, including medicine study in this application. For example, in the CT and MRI imaging, we could learn operator for the phase retrieval, for image processing, for solving inverse problem. In learning the governing law for data in medicine, we could also try to learn the prediction operator, which is essentially equivalent to learn the dynamical system that can help us to understand the physical system very well, so that we can apply this knowledge to a more concrete application like drug design or understanding the dynamical system. In all these learning problems, they are usually high-dimensional problem or even infinite-dimensional problem. You know, a function space is an infinite-dimensional function space. So the learning problem here is very challenging. In real application, if we want to minimize the computational cost to achieve a target accuracy, the difficulty in this learning problem is typically due to the infinite-dimensional learning problem. And also it might due to the fact that the unknown operator is highly nonlinear. And thirdly, a very important factor to be considered to minimize the cost is due to the data structures. In typical machine learning algorithm, people use a fixed size neural network to solve the learning problem. For example, if we have this neural network kind of method is expensive if we have different data structure. For example, if we train this neural network with a certain data set discretized according to a certain discretization format, then if we want to apply it to another discrete data set, which is from another kind of discretization, then we cannot directly apply the trained neural network. Sometimes we have to repeat the expensive training again so that we can apply it to new data set. So if we can design discretization invariant learning, then we can avoid the expensive training step. Probably we have a question in chat. Oh, no question. Okay, so this is the justification why we want discretization invariant due to the complicated different data structures in real applications. Okay, so today I'm going to talk about some operator learning algorithm as the first part of my presentation. My idea to achieve discretization invariant in operator learning is to design some encoder-decoder that can capture the sparsity of the machine learning problem. So let me explain the figure here. this is a general idea to describe the basic building block of my neural network for the operator learning. We have an encoder that can encode a function u in the x domain to a finite dimensional vector. And then we input this vector to a deep neural network, after which we have another finite dimensional vector. We want to find a decoder that can decode this finite dimensional vector to a function v in the y domain. We want to train the parameters in the decoder, encoder, and also in the deep neural network, such that the composition of these 3 steps can approximate the unknown operator very well. So this is a basic building block of our idea. You know, this is a problem from infinite dimensional domain to infinite dimensional domain. If we don't have any sparsity in the learning problem, then it is impossible to have a high accuracy. So our assumption is that the unknown target operator has some sparsity structure, and we want to design encoder and decoder that can capture the sparsity structure. So in other words, to understand this requirement intuitively, we want to make sure that we have good encoders such that for the functions in X we are interested in, this encoder can encode this function to finite dimensional representation without losing much information. And we have the same requirement for the decoder. The decoder can capture the sparsity such that it can decode finite dimensional representation to functions without losing much information. And we hope that with this encoder and decoder, the original learning problem can be reduced to a learning problem from finite dimensional domain to finite dimensional vector to a finite dimensional vector. And we hope that due to the powerful expressivity of neural networks, we can find appropriate parameters of the neural network to learn this mapping. So what is a deep neural network? From the mathematical perspective, I think it's very simple to understand. It's just a special way to generate a function parameterization using the composition of simple nonlinear function. For example, we have nonlinear functions hi, which is the composition of a linear function in U, after which we have a vector. We apply a nonlinear activation function sigma entry-wise to each entry of the vector wu plus b. So this is a very simple nonlinear function because typically the activation function we choose is very simple nonlinear function. For example, the red rule function, which is the max of 0 and x. It's a piecewise linear function. But even though the nonlinear function hi is very simple, after a few layers of composition, like L layer of composition, and finally we have a linear transformation T to generate a complicated neural network function psi, we will see later that this new class of function generated by function composition is very powerful to approximate high dimensional function to very good accuracy. So deep neural network will be applied repeatedly in the design of my network. I will briefly discuss the idea to apply deep neural network to design the encoder and decoder in the scheme in the basic block here to illustrate why we can get discretization transformation that can transform U to a finite set of a finite dimensional vector, and also get the transform the finite dimensional vector to V with discretization invariant. So what is discretization invariant? Essentially, it means that no matter how we discretize a function U, we can apply our mapping to this function U to generate another function V, no matter how we discretize this function V. This is so-called discretization invariant. So let us look at the transformation we design here as a mapping from the function u to the function v. We use a neural network to parameterize the phi1 function. So no matter how you discretize the function u, as long as we know the discretization of the function u, we can discretize the integral into a matrix vector multiplication adapted to the discretization in u and in v, so that we can simply carry out the matrix vector multiplication representing this integral transformation to compute v from u. So this is how to achieve discretization invariant. For the transformation from u to v as the encoder, similarly, we apply this idea to get discretization invariant decoder computing u from v. So this is the basic idea to get discretization invariant encoder and decoder for the basic idea in this figure. And because we have reduced the u function and v function to finite dimensional vector, so next we just apply a typical deep neural network to map from a finite dimensional vector to another finite dimensional vector. And why we want to design this kind of integral transformation as discretization invariant encoder decoder? We can understand this idea from some point of view of traditional data science algorithms. So we can show that neural network is very powerful to approximate any continuous function. So this means that the neural network we apply here can approximate, probably we can train neural network to approximate Fourier transform, ray Fourier transform, or other useful integral transforms in computational mathematics. So this means that our encoder can be very powerful to probably include all kinds of integral transformation you have. So if we can use training sample to train a powerful neural network to get the data-driven integral transformation, we probably can capture the sparsity of the learning problem so that we can get good result. You can also understand this neural network integral-based method as the neural network-based PCA. You can understand, after discretization, the neural network here will become a matrix. And after discretization, the function u here will become a vector. So the matrix vector multiplication can be understood as computing the coefficient of the given function u using basis function as the rows of this matrix generated by the neural network. So you can also understand this kind of projection as the PCA. If we have a u function, we can use PCA doing a matrix vector multiplication to get the coefficients of the PCA. So we just have a data-driven method to learn the best possible integral transformation to get the PCA transformation. And finally, we try to use the basic building block in the slide here to form a deeper and wider neural network in our application. For example, we use the basic building block in some parallel format where we have the idea inspired by the time frequency analysis. In the time frequency analysis, we know that sometimes solving a problem in the original domain might be difficult. If we compute the Fourier transformation to look at the problem in the frequency domain, then it's probably easier to solve. So this is a very naive idea. And inspired by this naive idea, given the input function, we keep the original function and as well as the Fourier transformation of the function. We apply these two functions to two individual blocks, basic building blocks. And finally, we combine them together and apply a very small neural network to post-process the result to get a basic building block like the block here. If we repeatedly apply this building block for L times, we can build our final network. Of course, you can also apply Rayford transform or other transformation to get other data representation and apply other parallel blocks. This might be interesting future work. This is how we build our deep neural network. And finally, I would like to emphasize some innovation in our loss function design. Recall that our objective is to get discretization invariant. So it is very crucial to make sure that our learning precision can make the neural network have some sense of different data structure. So we have the typical least square loss function here, trying to quantify how good the neural network size is to compute the result for given sample U to get the output value V. This loss function L can be chosen as typical MSE loss function. So you can see that it quantifies how good phi U to predict V. To achieve discretization invariant, we also augment this loss function with another term here, whereas it's a random interpolation operator, randomly interpret the function U and V to other sizes, other discretization format. So with the augmentation of this loss, this regularization, our learning can see different data structure in the learning process. This is a very crucial idea to get good performance. Finally, I would like to present some numerical results of the proposed algorithm compared to state-of-the-art algorithms. First, UNet, it's a deep learning method for audio signal processing. It is not discretization invariant, but for the purpose of comparison, I will also compare it. And you will see that the training of UNet will be repeat if we apply it to different discretization sizes. And hence the computational cost for UNet is much more expensive than our algorithm. DeepONet it's some algorithm proposed for operator learning, but in the naive version of DeepONet, it is not discretization invariant. So repeated training should be repeated again if we have different test data. The FNO, it's probably the first method emphasizing on discretization invariant, and the Fourier transformer and the Colloquium transformer are new algorithm proposed recently for this discretization operator learning. We are going to compare all these algorithms in 4 different applications areas, like for prediction, for forward problem, inverse problem, for numerical PDEs, for signal processing, for healthcare data. In the first example, we talk about the prediction about the future state for the Burke's equation. So we have a nonlinear PDE, the Burke's equation. The problem is that given the initial condition, we want to predict the solution at the future time step, for example, time t equal to 1. We are going to solve the Burke's equation using traditional software like finite element or finite difference solvers to get very accurate solution. And once we have this accurate solution, we can train our neural network using this accurate solution. After training, next time, if we have a new condition, initial condition, we don't need to use traditional software to solve it again. We can apply neural network to this condition to quickly predict the solution yield at the future time step. So the application of neural network is very cheap, but to be honest, we rely some traditional software to get the training data. So in the first example, we use high resolution data to get the training data, and then we downsample the training data to get low resolution data to train. For example, head S represent the grid size of the problem. We train our neural network using grid size equal to about 1,000, and we test our trained neural network with other grid sizes. In other words, the test data have this different discretization format. As you can see, all these methods roughly have the generalization ability to generalize to other discretization format, even if we just use s equal to 1000 to train. The test error for other grid sizes are reasonably small, essentially equal to the test error for the training data set. And our method is almost the best. It's only worse than the Colloquium transformer and Fourier transformer. But I would like to emphasize that if we increase the number of training sites to 10,000, then we can see that our method is the best method. This is the performance of FT and GT is worse. It is a little bit surprising. You know, if number of samples is larger, their performance will be better. However, their performance become worse. The error increased from 0.1 to 1%, 0.1% to 1%. This is something weird. And the second example is to solve forward problem. So we have parametric PDE, where we want to learn a mapping from the parameter function A to the solution function U. We also use traditional solver to get one true solution and downsample the solution to grid size equal to about 141 to train our network, and apply our train the network to other grid sizes. As you can see, we have almost the best accuracy, and we can achieve generalization, very small generalization error to different data structures. And a more challenging example might be the inverse scattering problem. In the forward problem, you might argue that it's a well-conditioned problem, it's easy to solve. And now we look at a challenging problem, which is ill-posed. We have an inverse scattering problem. We have a Helmholtz equation with some coefficient C that is not known, and we want to recover from the measurement of the U. By rearranging this Helmholtz equation, we can get a very special Helmholtz equation where the operator L null is known. It's given by the operator here, where C null it's a known function in real application. So our job is to recover the coefficient eta from the measurement of the solution U. So this is operator learning from U to eta. We apply traditional solver to get training data. We train the neural network using grid size S equal to 81 and apply the neural network to other grid sizes. As you can see, our method in this example works quite well to get almost the same accuracy, except the last one, where we have a very high frequency problem. So the test data for this problem is very far away from the training data. So that's why we have worse performance. But this accuracy is good enough for typical inverse problem applications. The other algorithm, they all failed. The errors measured by the relative L2 norm is not meaningful. And finally, I would like to present a healthcare application example where we want to analyze ECG signals. This is a standard bright source separation problem in signal processing. We have measurement from the mother, and we have the activity of the heart of the mother and also activity of the heart of the fetus. So the measurement from the mother contain information from the mother's heart and also the fetus heart. So our goal in this problem is to decompose the measurement into three parts: into the ECG purely from the mother and the ECG purely from the fetus, and also possible noise. So our learning problem is given a one-dimensional signal. We want to map it into three different signals. And we apply all different kinds of deep learning method to this problem. We also apply UNet in this example because UNet is the state-of-the-art deep learning for music signal processing. It can decompose music signal into different components according to different instruments. So according to the table here, our method is the best compared to other methods, and other methods does not provide meaningful results if we have different discretization format. So that's all for the numerical algorithm part. And finally, I would like to briefly discuss the theory part of the talk. In the theory part, I just realized that there's limited theory for this kind of operator learning. I can only find 2 papers online. The first paper is written by the group at ETH and also Brown University. It provides a posteriori error analysis for the ONET, which is not discretization invariant. The second paper is developed by the group at Rice and Caltech. They discuss some non-deep learning approach for learning linear operators. So this motivates our work to provide a priori error analysis for nonlinear operators with possible discretization invariant features. Let us focus on the analysis of our basic building block without repeating application of these to get a very deep neural network, because we can use this as a first step to analyze operator learning. You can extend the result for this setting to more complicated setting if we want to repeatedly apply this idea to get deeper neural network. The second reason is that this framework already includes several examples of algorithms in the literature. For example, traditional solver, where we use fixed size neural network to learn a mapping from finite dimensional space to finite dimensional space, we can understand this kind of method as a very special case for this general framework when we use some basic expansion to construct the encoder and decoder. For example, original learning problem is from a function space X to another function space. If we use finite dimensional basis to expand these functions, then we can reduce a function to a finite dimensional vector, like the expansion coefficients. So once we have reduced it to finite dimensional problem, then we can use a fixed size neural network to learn the mapping. And this general framework also includes the so-called PCA-net, developed by the group at Caltech, where the encoder and decoder are PCA. And this framework can also be understood as a framework that includes a deep ONET if we consider the encoder as function sampling to discretize a function u by evaluating the functional value at discrete samples, and consider the decoder as deep neural network based PCA. And we can also use this framework to understand one block of our learning algorithm. Okay, so in the theory, we have such problem setting, like we want to learn a non-operator psi. We want to have the composition of encoder, fixed size neural network, and decoder such that it can approximate the non-operator psi accurately. So how can we learn this operator? We assume that we have Lipschitz operator. We assume that we have some training sample generated by the unknown operator. We consider a two-step learning algorithm, which is also the case in many existing algorithms. In the first step, we use half of the data sample to learn decoder for the X space, decoder for the Y space. And in the second step, we use the other half of samples to learn the fixed size neural network through regression. For example, in the empirical risk minimization, we want to find the neural network gamma such that the composition can learn the mapping from U to V, essentially the mapping of the unknown operator psi. after solving this empirical minimization problem based on finite sample, which we will wonder how good the solution is. For example, we have the global minimizer of this empirical optimization problem. We wonder if we substitute this minimizer to construct a neural network, then how good the composition here to approximate our original target unknown function, unknown operator psi, to have some accuracy measurement. We try to use the so-called population risk that consider the learning accuracy for the learned operator psi theta to approximate the target operator psi, considering all the possible data in the domain of the operator. So this is the population risk. It is a reasonable risk to analyze the data. And our theoretical problem is to see how good the empirical solution is according to this error quantification. So our problem is to quantify the error for the global minimizer of the empirical loss function quantitatively. Our goal is to quantify the error in terms of the depth and the width of the neural network, and also the number of samples to guide the design of the size of the neural network and to guide the design of the choice of number of samples in real application. According to our theory, you probably also understand when and why we could avoid curse of dimensionality in this kind of learning problem. The curse dimensionality is important because by definition, the curse means that the number parameter is exponentially large in the dimension of the problem, and the number of samples is exponentially large in the dimension of the problem. So if we have the curse, then the learning is very difficult. If we don't have a curse, then we can use relatively small neural network with relatively small number of sample to solve the problem with a good accuracy. And we can also see why we can get good generalization to different data structures according to our theory. And how many time do I have?
7 minutes.
Okay. So I think it's enough. So the analysis can be decomposed to the so-called bias and variance analysis according to standard statistical learning method. The goal is to quantify the error according to the population loss. We can decompose it into two parts, T1 and T2. The T1 part is called the bias part. It can be addressed by approximation theory of deep neural network, because if we can prove that we can have neural networks such that the composition here can approximate an unknown operator at all the possible sample location, then of course all the terms here can be very small. So T1 can be small. And as for the T2, it's called the variance related to generalization error from finite sample to all the possible data following some certain distribution. Essentially, it is the error where we use the average of some sample to approximate the expectation according to some distribution. So this is the variance part of statistical learning. So in the first part, we look at the approximation part, and we can prove that the T1 part can be bounded by the following equation in the second equation, up to some noise perturbation and some encoding error. So the crucial part is to analyze the size of this. And what is this term? Essentially, we have a known operator in red. We want to find a neural network gamma such that it can approximate this unknown operator in red, evaluated at the data sample in blue. So the bound of T1 can be transferred to the bound of the approximation power of a neural network to approximate some functions. And in particular, we care about the curse of dimensionality. We care about how good the error is in terms of the width and depth to guide the design of neural network. There has been some existing research for approximation theory, but unfortunately, there's no theory to quantify the error in terms of the width and depth. And the understanding for curse of dimensionality is also quite limited. So this motivates our work to quantify approximation error for deep neural network. We saw that for high dimensional continuum function, if we use rule neural network with width n and depth L to approximate this continuum function, the nearly tight error rate is like this, where W omega f is modular continuity. Due to the term 1 over d here, we can see that we have the curse of dimensionality. And unfortunately, even though we reduce the function class from continuum function to CS function, the smoothness cannot help to reduce the curse of dimensionality. This is some bad news for rule neural network. But the good news is that, as we shall see later, we can apply some other structure in the target function to get rid of the curse of dimensionality. The study of the red rule motivate the study of other activation function, because we have a curse where we use the rule activation function. Then we recently discovered that if we use some simple activation function like the function drawn in the figure here, then we can avoid the curse of dimensionality. We can prove that with a fixed size, like order d square width and order 1 depth, we can have a neural network approximating any d-dimensional continuum function within any small accuracy. So only the parameters of this neural network depends on the target function and the accuracy. The size is independent on the f and the accuracy epsilon. So there's no curse in this kind of approximation. But unfortunately, because the pseudo dimension of this neural network is infinite, as we shall see later, we cannot apply this kind of approximation result in the generalization analysis. So we will derive some generalization bound based on rule neural networks in the second part for the variance estimation. And the result for the variance part for operator learning is also quite limited. I don't see any good result on this. People might have some partial result. And recently we provide some result on the bound of T2 part. The idea is to follow the roadmap here. We can bound the T2 part, the variance part, using some covering number of the class of neural network. And then we can use the pseudo dimension of the neural network to bound the covering number. And finally, we can use the size of neural network to bound the pseudo dimension to get the final bound for the T2. So recall that in the very powerful neural network, because the pseudo dimension is equal to infinite, so that means that we cannot use that powerful neural network in our generalization analysis, because if we have infinite, then the error bound is meaningless. So first, we develop some mathematical analysis to use the covering number to bound T2, and then we applied the analysis by Peter Bartlett to use the pseudo dimension to bound the covering number. And we also applied the result by Peter Bartlett to use the size of neural network to bound the pseudo dimension. And finally, we combine all the results together to get our final theorem. In our final theorem, we prove that if we use neural network of depth L and width n, then with number of sample scaling like this, we can get the generalization analysis. So in other words, the accuracy of the operator learning can be quantified by the error terms here. If the number sample is sufficiently large, if the encoder and decoder are accurate enough, then we have good accuracy. But we do have curse dimensionality because dx might be very large. So this motivates us to consider some low-dimensional structure. For example, if we assume that after encoding, data lie on low-dimensional manifold, then we can get rid of the dx. Instead, we have a very small d0 to avoid curse dimensionality. And if we have low complexity model, for example, this is typical model in statistics, then we also can get rid of the curse of dimensionality. We have a small d node representing the complexity of the model. And that's all. Thank you. I would like to thank my sponsors for supporting my research to build my diverse research background. Thank you very much.
Okay, we thank Haizhao for an interesting talk. Well, since we already run out of time, maybe we can just have a couple of quick questions.
Can I ask a question?
Okay, yeah.
Hi, Haizhao. Very good talk. So I'm wondering to know whether you can explain that why you can achieve the discretization invariant according to the theory.
Okay, thank you. This is a very good point that I need to emphasize for the algorithm design. So as you can see in our full error analysis, we have designed discretization invariant encoder and decoder, meaning that no matter how you discretize the function u, you can still apply our encoder to the function u. So as long as we have trained the decoder encoders accurately to do the data compression, then the accuracy, the error term for the encoder decoder for the space x and y will be very small. So this is how to achieve the discretization invariant by training data-driven encoder-decoder to capture the sparsity structure of the learning problem to reduce the error of the encoder-decoder here.
Okay, thanks for the explanation. And also, can you give me some intuition that why you can achieve the discretization invariant in your real applications?
Yeah, that's a very good question. So the result here has a gap between theory and application. So I just have a very abstract framework to analyze the error in terms of number of sample n and the size of the neural network, depending on the number of sample n. So in real application, how can we apply our theory here to justify the algorithm in real application? This is a very good question and deserve future exploration. I can give you one simple example so far. So let us look back to the Burger's equation example. So it is well known that we have the Cole-Hopf transformation or so-called Hopf-Cole transformation that can transform the nonlinear Burger's equation to a linear problem. Essentially, we introduce another function v. There exists a nonlinear transformation from the u to the v, and then we can solve a linear question for the function v with initial condition to get the function value v at the later time step. And then there exists another nonlinear transformation transforming the function v at the later time step to back to the u function. So in here we have 3 steps. One nonlinear transformation transforming the initial condition, and then solve a new linear problem, and then another nonlinear transformation to transform v at time step 1 to u at time step 1. So these three steps can be considered as a nonlinear transformation, transforming to the function variable u at times equal to 1. And interestingly, this nonlinear transformation can be understood, can be proved to be the model that we have analyzed here, where we have the multi-index model. We can prove that the nonlinear transformation introduced by the Kohl-Hopf transformation can be understood as a multi-index low complexity model in the learning operator. So the unknown operator mapping the initial condition of u to the future state of u can be proved to be the model we consider here, so that we can avoid the curse of dimensionality in the learning problem for the Burger's equation. If we want to extend this kind of research to other cases, that would be very interesting future research.
Okay, thank you. Thank you. Thanks for the answer.
Okay, any other question for the speaker? Yeah, when you said your method is kind of the best when you compare with other methods, I'm just curious if it has any disadvantage, for example, a higher computational load, particularly when your training size increased to 10,000.
Yeah, that's a very good point. So in the comparison here, I would like to admit that this is not a very fair comparison, because we haven't considered the number of parameters in all these different models. The number of parameters in our method is larger than the other models. So this might be some unfair comparison. But I would also like to emphasize that even though we increase the number of parameters in other models, their performance cannot be improved pretty much. So in our comparison here, we just simply use the accuracy as the single criteria to tell you which method is better. And in the future, we also have some plan to speed up our computation. We have some dense matrix computation coming from the kernel here. In the future, we would like to discover some fast algorithm to implement this matrix vector multiplication to speed up the calculation. That's all.
Okay, thank you. Okay, well, if there are no more questions, let's thank the speaker again.
Thanks a lot.
Okay.